Cool. Okay. Good morning, everyone. Welcome back to Big Data. To what is the, I guess, penultimate lecture of the semester. The plan for today is to wrap up the discussion of Bigtable and HBase and move on to the decentralized distributed key value stores, specifically to look into Cassandra. Okay. Pasted the Slido link in the chat. Feel free to ask any questions you might have on the Slido. Okay. So let's then try and link to what we were discussing last time. So we said that Bigtable or HBase is practically an LSM tree, a log structured merge tree implementation on top of files that are otherwise stored on HDFS. In this picture, we can see all of the basic, all of the core building blocks of HBase. Each one of these has, of course, a counterpart in Bigtable. So we have the client, we have the master, we have the zookeeper, which is this distributed logging service that is also used to store some of the metadata of the system. And then we have a bunch of region servers being the equivalent of data nodes on HDFS, the master being the equivalent of the name node of HDFS. And what happens is that the region servers practically implement the logic of the LSM tree. So they have the in-memory store, they have the write-ahead log, they maintain the spill files, but the data that is persistently stored, so the H log and the files, these are actually files on HDFS. So from this point of view, HBase is a client to HDFS. Yeah. And the way interactions typically work is, you have a client. The client wants to access some rows. So the client comes to you with a table name, a row key, and possibly other constraints like a column family or column names and so on. So first thing that needs to happen is for the client to find where the data it's looking for lives. So it needs to somehow find the correct region server that is handling the region for that tablet that the client wants to access. Okay. Once the region server has been located, what the client will do is it will communicate directly with the region server, ask for, let's say, the row key it wants to read. And what the region server does is exactly what we were discussing the past 2 weeks for LSM trees. So the region server will check its in-memory stores to see whether what we want is already there. It will also check its in-memory caches that are not visible in this figure, the block cache we mentioned last time, to see whether any more information is there. And if it can decide that everything the client needs can be answered by just the mem store and the cache, it will respond directly to the client. Otherwise, it will have to go through the appropriate spill files. And for that, it will do all of the tricks we were discussing in the past. So it will look at the Bloom filters that are attached to the store files, to the H files, to check whether what the client requests could be in each one of them. And those that give a positive response through the Bloom filter, it will go and look at their block index to seek directly to where the data would be if data is actually in that H file. And then it will assemble all of that in main memory and return the result to the client. And keep in mind that as it goes through these H files, whenever the region server wants to read an H file, we said it needs to go and read the Bloom filter, right? So it will have to go to the data node, so to the name node, see where are replicas of that block stored on HDFS, then go to the respective data node to get that data, bring it back into memory, cache it somewhere, check, and then go back and down and up and down and up as many times as is required. Okay. In case this sounds like a lot, that's exactly the reason why we have a cache in the region server, because with a cache we can avoid quite a few of these round trips, because typically access patterns exhibit locality. So typically when a client asks for a row, there is a high probability that the next time someone will ask for something, like the next time a client will ask for something, it will ask for a row that is next to the one it asked previously. So the same metadata would still be useful. Maybe even the same blocks would still be useful. Okay. There's also temporal locality here, but that's sort of orthogonal. So some of these rows will probably be more frequently accessed than others. A typical example here is if what you store in HBase is something like, let's say, a social network, then the row for the very highly popular people in this network will be accessed way more frequently than the rows of less popular people. Okay, and so these caches play a big role in alleviating some of these latencies. Okay, now I think we didn't cover what this is or exactly what work it does, and we need still to address the problem of how we detect failures and how we react to failures. Okay, so I think this slide we saw it last time, but in any case, this guy Chubby or Zookeeper is this distributed service. It's pretty much a small cluster of its own. So you have a number of servers in this group of servers. You might see the term replicas, you might see the term server in an ensemble. It's all the same. You just have that many servers, all of which are supposed to have exactly the same data. Okay. Typically, you have an odd number of replicas, because whenever in doubt, these servers will vote for what is the correct state. And since they vote, you need an odd number, otherwise you would have ties. Again, typically these guys run in a master follower mode. So one of them is the master. All of the rights are given to the master, and the master then replicates each state machine to the followers. The master is not predefined. Any of the, let's say, 5 replicas can be a master. These replicas, they vote for who the master should be. Okay, and if the master goes away or is slow or whatever, they will vote for a new master, and the master will take up. As I said, these guys vote. A different way of saying that they vote in distributed systems is that they have a quorum. Okay, so if 3 out of 5 replicas, or 4 out of 8, or 6 out of 11, and so on, if a majority of the servers agrees on a state, then that is the state of the cluster, and those that do not agree will need to be updated to also agree with the others. Chubby, which is the Google version of this system, uses an algorithm called Paxos. I think I've posted a couple of links on the Moodle forum on Paxos. Paxos is one of those algorithms that you can understand its basic form fairly easily, but once you get to the more complicated nooks and crannies of the algorithm, such as how it handles specific failures, how it handles latencies and so on, then it gets a bit more complicated. Paxos is not part of the, it's not an examinable part of this course. Zookeeper uses another algorithm, another protocol called ZAB, that is sort of a simplification of Paxos, again, not examinable in this course. Okay. The key thing to take away from this is that you have these guys they sit on the side. They're not necessarily the same servers as the region servers and your data nodes and so on. Although in small deployments, if you have a cluster that only has 5 nodes, well, those 5 nodes will be your data nodes and your region servers and your Zookeeper servers and so on. For larger deployments, you typically want these guys to be separate so that they make up a failure domain of their own. Okay. All right. And we said that we have the masters and tablet or region servers, and that they do different things. This is all things we saw last time. I won't go over them again because we need to address a couple of other things. First of all, how do we locate the table that we want to read? So you have a client. That client comes to you with a row key, okay, and you need to take that row key and map it down to a tablet on a specific tablet server or a region on a specific region server. So what the client does is it goes to Chubby or Zookeeper and requests the location of something called the root tablet. Okay, the root tablet records the locations. So it's a tablet. It's like a table in Bigtable or HBase, yeah, that records the locations of the metadata tablets. Okay, so you have this other table called metadata, let's say. It's made up of tablets, regions. The locations of these regions are recorded in this tablet or in this table. Okay, and each one of these of the rows in these tablets records the location of a user table, actually the tablet of a user table. So if you want to read row 100 of user table N, let's say, the client would go to Chubby, would say, okay, Chubby, where is the root tablet located? It would get back the location of the root tablet, and that location is actually just the name of the region server serving this tablet. Okay, by name I mean IP address and port and so on. So then the client would contact the region server and ask for the location of the metadata tablet that would store the row for whatever table it wants to access. So user table N. So it would go from here to one of these tablets, and from there it would get the locations of all the regions of the table it wants to access. Now, given that these regions, remember, these are horizontal cuts in the key space. It would go and say, okay, into the region. Let's say it's key 0 to key 80. Okay, so it's not there. It's in the second region, and so on. And it would be able to do that by just reading this tablet here. Okay. So then it would eventually identify which region it wants to access, and then it would what it would get back would be the again name or IP address and port number of the region server serving that region. And so it would then go and access that region server and ask for the actual data it wants to get. Now, people might look at this and say that this is too much. Like, so there is one round trip to Chubby, one round trip to get the root tablet, one round trip to get the metadata tablets, maybe possibly more than just the one, and then one more round trip to get to the region server where I will request my data. And that's true. I mean, this is too many round trips. But what saves us here is the same thing I just mentioned a few minutes ago, locality. So what happens is that the client caches all of this information as it goes through this structure. So it will cache the location of the root tablet. It would cache the locations of metadata tablets. It would cache the locations of the tablets it accesses. And these things, they do not change that frequently. The only reason why the location of a tablet would change is if that tablet grew too large and it had to be split, or it grew too small and its adjacent tablet is also too small, and so they would need to be combined, or if the tablet server died and that tablet would need to be moved to some other tablet server. Okay, and typically you don't have these things happening all that often in an operational cluster. So with whatever client wants to read this data would need to pay the cost of these round trips once, and then with high probability for the duration of its life, wouldn't have to go through this again. Okay. Right. Okay, so this just explains what we were discussing. So let's go and see what the big picture is, right? So first of all, we need to locate which tablet server we need to access, and we need to do these round trips and then cache the data and so on. Then once we've gotten to the tablet server and we request a row, that tablet server will need to go through its spill files, its SS tables, and look at the Bloom filters to see which of those might contain the data we're looking for. Yeah. There is an intermediate step here that says, look at the in-memory caches, so the mem table and the block cache. But let's say that the data is not there. We need to go through the SS tablets. So first we go for the Bloom filters, and then once we've identified those tablets, so those regions, so those SS tables, actually, those SS tables that might contain data, we use the block index to seek in them and read the data we're looking for. Okay. Now the check of the Bloom filters, the check of the index block, this all happens transparently to the client. The client just asks the region server, and the region server will run the LSM read protocol that will need to go through these BFs, the Bloom filters and the block indexes. Right? That's not visible to the client. It's not the client that goes through the Bloom filters and the index blocks. Okay, so next question is, how do we assign tablets to tablet servers? Remember, it's the master who knows what tablet servers are around, what tablets have been assigned to them. The master can also know what tablets are not assigned to anybody. For example, a tablet might have been assigned to a server that just died, and so no one is handling that tablet. Okay. So what the master does is it tries to assign tablets to servers that have room. And by room, I mean that tablets that have, servers that are not overloaded. What it actually tries to do is to make sure that all tablet servers serve the same number of tablets, more or less, or all region servers serve the same number of regions, more or less. Okay. So how does this work? This all goes through this guy, Chubby. When a tablet server starts up, when you start the tablet server and you add it to your big table cluster, what the tablet server does is it communicates with Chubby, and it creates a log file in a directory called servers and takes the log on it. Okay. So Chubby, remember how Chubby is this distributed logging service, can also be used to store small metadata. The way this metadata is exposed to the outside world is through this file system like abstraction. So you have like directories and so on. You don't actually have directories. I mean, the directory is just a part of the name of whatever you store there. So the tablet server wants to create a log that is specific to the tablet server. So it will go and add a log under the server's directory with its name, and then acquire the log. Okay. The master now monitors this server's directory. So every time something happens there, every time a new log, for example, is added, the master will see that. And that is the signal to the master that now we have a new tablet server in the cluster. the tablet server will need to reacquire this lock. So this isn't actually a lock as it is a lease, right? You may remember we've had this discussion of locks versus leases in the past. The lock, you acquire it, and as long as you haven't released it, it's yours. If a tablet server acquired the lock and it died, the lock would remain locked forever. But a lease is something that you need to renew. So you acquire the lease, and the lease is yours for X amount of time. And within that X amount of time, you need to go and reacquire it, renew, reset the timer. Okay. Now, if a tablet server tries to acquire or reacquire its lock and it fails for whatever reason, it will just kill itself. It will leave the cluster. Okay. How could this happen? We'll see in a minute, or when this would happen. When a tablet server terminates gracefully, when the administrator will go and run the script to shut down the tablet server, it will go and release its lock. Okay. Okay. So let me see. Maybe I should explain it here. So there are some failures that we need to think of here, right? Let's assume that Chubby will never fail because it's this ensemble of several servers. You need to lose all of them for Chubby to go down. So what might happen is that either the tablet servers or the master have some problem. That problem could be that the tablet server or master has crashed, or that they are too slow, or that they have lost connectivity to the Chubby service. Okay. So what would happen if one of the tablet servers is in this duress? So if the tablet server cannot renew its lock, the master understands what's the situation of the tablet server by checking the status of its lock. Okay, it's not like talking to the tablet server. The master will check the Chubby service to see, is there a lock there for this tablet server? Is that lock, or this lease live? Has it been renewed recently? If it hasn't, then what the master will do is it will acquire the lock for itself. Okay. And what this means is that the meaning behind this action is that now I consider this tablet server to be dead. All of the tablets that were assigned to this tablet server, I consider them to be unassigned. And the reason why it acquires this lock is to disallow the server from going back into the cluster without asking the master first, let's say. Okay, it's a safety precaution because things might have happened. So if this tablet server goes away thinking I'm the guy who's responsible for tablet X, and while this guy is away, that tablet X is reassigned to some other tablet server, and changes have happened to that tablet. Okay, and then this failed tablet server comes back. If we didn't have this protocol in place, it would think that it's still handling that tablet, and it might go and do any type of changes to it, and that would lead to inconsistencies in the data. Okay, through this protocol, if a tablet server goes away and the master notices it before it comes back, then that tablet server won't be able to just go and resume its operation. Okay. So yeah, in essence, if the master succeeds to get that lock, meaning that the lock has not been renewed within the deadline of the lease, then that means that either the tablet server is down, or for whatever reason it's like slow or unable to talk to Chubby. In either case, the tablet server is as good as dead. Okay, so it will never serve the tablet again. Never is probably too strong of a word. It will not serve that tablet unless it comes back and it's fully operational and no one else is handling that tablet. Okay. So what the master will do then is it will delete that log file from the server's tier, meaning that that tablet server is as if it never existed. And all of the tablets assigned to it will be marked as unassigned. And now what this means for the master is that it needs to go and find tablet servers with space to serve these tablets. Now, what happens with the master? When the master starts up, it needs to find what is the current tablet assignment and to deal with any unassigned tablets. Yeah, that also happens through Chubby. So when the master starts up, it goes to Chubby and acquires a unique master log. Okay, there's only one of these logs. It's not like the tablet server logs. And the reason why there is only one is to make sure we will never find ourselves in a situation where we have multiple masters active at the same time. Okay, so the master acquires this master log and goes and reads the servers there in Chubby, and this tells it who are the region servers in the cluster, right? All of their IP addresses, port numbers, other metadata about the servers, and when was the last time they renewed their lease. So by knowing where to find them, it will then go and talk to all the tablet servers to find all of the tablets that they think they are handling. So these are all the assigned tablets, okay? And once it has done that, it will go then and scan the metadata table. Remember, we saw the metadata table a couple of slides ago, and that will tell it what are all the tablets. And by taking the difference between these two sets, it will know which are the unassigned tablets. Okay. Okay. So when we want to do any change to the tablet, what happens? When a tablet server receives a write operation, first we'll go and check with Chubby to see whether that write can actually go ahead, whether the user is authorized. It will then write whatever change it needs to do in the memory store and append it to the write ahead log. Okay. When the and actually, just to make this clear, these two changes happen in this order. First, you add something to the log, and once it's in the log, you can append it to memtable. Okay. When you receive a read operation, you check Chubby for authorization. You check your in-memory caches like your mem store, your block cache, and if you cannot answer the request from just those guys, you need to create this merged queue. Okay, so you need to pull together whatever you have in memory, go through all your SS tables, and assemble the answer to the user request. Okay. All right. And that's all on Bigtable and HBase. Any questions before we move on to Cassandra? Okay. Don't see any questions coming in Slido. I hope this thing works. Yeah, no questions there. Okay, good. So I take this to mean that we are good with HBase and Bigtable and move on to the second thing for today, which is Cassandra, or decentralized key value stores. Okay. So Cassandra was, just a quick history here, was built by Facebook for Facebook several years ago. It was built to support Facebook's inbox search, and the requirements were that this thing should be able to support billions of writes per day. It should be able to support concurrent. This should be concurrent with reads from roughly 250 million users back then. And this was like this until 2010 when HBase was adopted. What's the situation now? not really sure. Haven't checked with them lately. So Cassandra was released as open source in 2008, became an Apache project in 2009, top-level Apache project 2010. And then there was a company called DataStax that was founded in 2010 around this Cassandra system to commercialize it, just like, let's say, Databricks was created to commercialize Spark. Okay, Cassandra is deemed one of the fastest key-value stores out there, and it has actually been the inspiration for quite a few other systems. Okay, let me see. So what were the design desiderata here? First of all, they wanted a system that has no single point of failure. So there is no master, no predefined master anywhere. Okay, and this is in contrast to everything we've seen so far. Okay, this is the difference between distributed and decentralized. A distributed system is one where operations happen in a distributed manner. So your data is spread across multiple nodes, processing happens across multiple nodes, and so on. But there might be a mastermind. In a decentralized system, again, you have distributed operation, but you have no mastermind. The data model is, again, table-like. It's not a relational database. It's just like HBase, right? So you organize the data in tables, being made up of rows and columns and column families and so on. It was actually required to be very highly scalable. We saw that it was used by Facebook. We can imagine why. But the extra bit here is multi-data center operation. So Facebook wanted this data store to be able to operate over more than one data centers. Is that possible with HBase or Bigtable? Yes and no. So when you are in this multi-data center operation, in this multi-data center mode, network latencies are much higher than within the data center. That means that now your lease deadlines need to become larger. That means the system is now slower to detect failures. And that means a lot of the performance that you would get out of a system like this would go down, okay, for a design like that of Bigtable and HBase and HDFS and so on. Cassandra has a somewhat different design. We will see what that looks like. It's highly available, and availability, as we've seen in the past, is achieved through replication. And it's providing high write throughput without sacrificing read performance. Okay. And here, replication can also be used to reduce read latency. So you can choose the closest replica and so on. So far, with the exception of this multi-data center operation and, well, the decentralized nature, the rest shouldn't be too new to us, okay? And that is because Cassandra has many influences. So it has it's heavily influenced from Bigtable and HBase in the sense that it also implements this sparse multidimensional map data model. It's also, let's say, borrowing some ideas from GFS, Chubby, and so on, even though it doesn't necessarily use them. It's also heavily influenced from Dynamo. Dynamo was a system that came out of Amazon. If you read the Dynamo paper, which is actually linked on the Moodle page of the course as extra reading material, you will find many similarities. To some extent, one could say that Cassandra was the Facebook version of Dynamo. And that's actually true, because what happened was that I think the best way to put it is that Facebook bought the team that, acquired the team that designed Dynamo, and they designed Cassandra for them. Okay, it's also borrowing some ideas from distributed hash tables. So the cluster organization and the partitioning of data across cluster nodes is borrowed directly from DHTs, distributed hash tables. And last but not least, the consistency that it offers is, it's base, so it's eventual consistency. We will see that Cassandra offers opportunities for tuning this consistency, so you can have higher consistency and lower the availability, or higher availability and lower consistency. And this can all be decided on a per request basis. Okay. So high write throughput. How do we accomplish high write throughput in Cassandra? Well, I think we know all the tricks that we can use so far. So we use an in-memory buffer for writes that avoids disk IOs. We have a write-ahead commit log to which we append the data first before writing to the in-memory buffer, and this gives us persistence and durability. We batch these updates to this write-ahead log and only do append writes. And what this does is amortizes disk writes to the write-ahead log, and also hides some of the latency of going to the disk. We know why append-only writes are a good idea. Yeah, no random IO, right? Okay. So this is all the same as in HBase. Okay. What Cassandra does, in case you didn't guess it so far, is it also implements an LSM tree. Okay. Okay. The data model is quite close to that of HBase too. So we have cells, so quadruples of row key, column name, timestamp, and column value. Yeah. And we have a create, read, update, delete API that comes straight from Bigtable HBase. Okay. The data unit here is a column, and that's what the cell is. And these columns are grouped together into column families. And then we have something that's called super column families. That is column families that can contain column families. For example, in the inbox search app for Facebook, we had a super column family for each of the words in each message, and then a column family per word, with each column being the message IDs that contain the word. And then if you had a query to look for a term, it would use these super columns, just like inverse index. Okay. Now, operations on a given row are atomic per replica. So this means regardless how many columns you access in one row, you are guaranteed that that update will be visible atomically. This is the same guarantee that HBase offers in Bigtable. Yeah. If you cannot see how this is accomplished, just think of what makes up a row, and when is the row made, when is this data made visible to the client. So we know that in this data model, every cell is this quadruple, where you have your row key, column name, blah, 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 timestamp, and then the value. And a row is merely made up of all of the cells in a table that share the same row key. So if you have a client that sends over an update, a write, for a row that has, this write has a gazillion columns in it. This write would be applied first to the write-ahead log. Yeah. Once it's applied, or once it's been appended to the write-ahead log, then we tell the client you're good to go, and the data is added to the in-memory buffer, the mem store. Clients that come to read data won't see that data unless it's already in the write-ahead log. So they will never see partial information. Either the data is all in the write-ahead log or it's not. Okay, so this gives us this atomicity. The API is again quite simple, borrowed from DHTs. So you can insert to a table data identified by a key, and then you give whatever you want to insert. You can get from a table data for a specific key, and maybe you can also define specific columns to get back if you want to filter. And then you can delete from a table anything under a key, or everything under a key and a column name. Okay. Now, since this system is decentralized, we need to have a way of talking to it, right? So a client would typically sit outside the system, and it would want to store or load data that would go somewhere in this big system. So how do we do this? Either the client needs to be able to run this distributed protocol of talking to different replicas, making sure that they are all happy and they all have the same data and blah, blah, blah. Or we play a trick, and that's what happens here. The trick is that for every request of a client, there is a single node that is chosen, possibly at random, or maybe not at random. Anyway, the client chooses one node in this Cassandra cluster, and then that node becomes the coordinator for that request. So the client will only see that one node. It will send its data to the node. It will receive the responses from the node. And that node will then act as a proxy of the client within the cluster. It will run all of these distributed or decentralized or whatever protocols within the cluster to make sure that the client's request is served. Okay. Now, how do we find data here? We find by using something called consistent hashing. And the consistent hashing is something that comes from now somewhat olden days of peer-to-peer systems. So in when was it? Early noughties. So just as the the century and the millennia turned, peer-to-peer file sharing systems were researched quite heavily by academia and industry. And I don't know how many of you have heard of these systems. Like there was initially there was Napster, but this was a music sharing service. It was a distributed service, so there was a centralized directory of which nodes stored and served which files, and the client you had as a user would connect to this directory. So let's say you want to download songs by, I don't know, pick a band, right? You would connect to this directory and ask it which nodes store the file you're looking for. And you would get back a bunch of IP addresses and port numbers. And then your client would connect directly to these other IP addresses and port numbers to download the files you're looking for. So you have your mastermind, but all of the heavy data communication happens across peers, right? Then there were other systems like Gnutella. Can't remember what was. So Gnutella was the protocol running behind the scenes. It was also the name of a system. And there were other systems that were using the Gnutella protocol, but they had different names. And Gnutella was completely decentralized. So every node in that system knew only the nodes around it, only its neighbors. And whenever you wanted to find anything, what you would do would be something called gossiping. Or in the worst case, broadcasting. So every node would send the request to all of its neighbors, and the neighbors would check whether they can answer the request on their own. And if they can, they would respond back to the peer. Otherwise, they would forward that request on to their neighbors, and they to their neighbors, and they to their neighbors, until the whole network has been flooded. There were some improvements to this that were going down just specific paths of the network, but that's outside the scope of this course. And then came the era of structured peer-to-peer systems, where the network was structured in such a way that would tell you exactly where to store this directory information that was, the Napster had it in a central place, and now we decentralize it. So this directory information of who stores what is now stored all over the place, all over the network, but in such a way that allows you to find it efficiently without having to flood the whole thing. Okay, and we'll see how this happens. Yeah, so this whole idea of consistent hashing is this. We'll see how it works. And this peer-to-peer design philosophy is there to make sure that there is no single point of failure, no master, and no global knowledge on which nodes are in the cluster, which data items are stored in the cluster, what is the load of each node, which are failed or non-responsive, and so on. Everything that the master knew for HBase, now we want this knowledge to be decentralized, right? We also want to make sure that whenever nodes join or leave, the cost is minimal. So we don't need to rehash everything, replace items all over the place. Okay. So let's see. Let's do a quick detour of these DHTs, these DHT overlay networks. Okay. The whole idea is that they expose an API that looks like a hash table. So you can put a value for a key, yeah. You can override data, but let's ignore this for now. I mean, let's assume that we always override, and you can get whatever value is associated with a key. Okay, typical hash table API. Now, what happens is that let me see. I think I have it in greater detail. Yes. So what happens is that your nodes, they are spread out over an ID space. Each one of them has an ID. This ID is drawn from an ID space. And each one of them also stores pointers to other nodes in the system, but not to all nodes, just to a logarithmic number of nodes, I mean, logarithmic to the number of all nodes in the system. Okay. And then you can go from any node to any other node just by going through these pointers. We'll see how this works briefly. Okay. So the typical interface just has insert, lookup, delete, update, and join leave for nodes. And this is where the magic starts. So every node and every item, okay, is assigned an ID in a circular ID space. So these are n bit IDs, so you get from 0 to 2 to the n minus 1. And the ID that's after 2 to the n minus 1 is actually ID 0, right? So this is a circle. And how are these assigned? You use a pseudo uniform random hash function. So you take information of the node, let's say the node's IP address and port number, you hash it, and that gives you the node's ID. Or you take an item, like a file or a row, whereas you hash it, and that gives you, again, an ID in this ID space. The fact that the hash function that you use is pseudo random means that your IDs are, again, pseudo uniformly distributed around the circle, around this this ID namespace. Okay. And the next step here is to assign items to nodes. So you have your nodes that are around this circle. They have assumed identities on this circle. Now you have an item that you want to assign to a node. Okay. And what you do is you take the item's ID and you assign it to the node whose ID is the first after the item's ID. We will see graphical examples in a few minutes. The second part of the puzzle is that whenever a new node joins a network, as it comes in the network, it might go in between two already existing nodes. And in that case, it will reclaim all items that would have been stored in its predecessor that should be stored in it, or in its successor in this case. Okay. On the other hand, whenever it leaves a network, it will send all of its items to its successor. So let's have a quick visual of this. Let's say, so we have these nodes, we have these items. We will try and place them on this circle, and this is the ID space here is 64, size 64. So M is 6. Okay. And let's say that what you see on the right side in these two tables, so this green stuff here, these are the actual IDs. So you've taken the IP address and port number of the node, you have hashed it, and this is the outcome. Okay, outcome modulo 64, of course. So a node comes in with this address, it computes its node ID, and this means this node is now this guy, node with ID 0. Okay, another node comes in with this IP address. The IP address is hashed. That gives a node ID, and that node assumes its position on this circle. Okay, and we do this for all the nodes. We'll see in a few minutes how these guys are connected. Okay, but for now, let's assume that these are the nodes we have. Okay, then when we want to place an item, we do a similar thing. So we take the items, let's say key, we hash it. That gives us an ID. And then what we do is we take that ID and see where it would fall on this circle. Okay, so ID 20 would fall somewhere here, but there is no node for ID 20. There's no node sitting on that ID. So what we do is we conceptually move forward in this circle until we find a node that that exists. Okay, so that is the successor of that ID. So the successor of all IDs after 9, so 10 up to 28, is node 28. The successor of all IDs from 29 up to 40 is node 40. Yeah, the successor of all IDs from 41 to 54 is 54, and so on. And the successor of all IDs after 60, so 61, 62, 63, and 0 is 0, because this is a circular space. Okay, so by following this, let's say protocol, we pretty much assign, again, conceptually at this stage, we assign these nodes, so these items, to the existing nodes. Okay. Now, if a node was to come and get an ID of, let's say, 21, so it would fall somewhere here. Yeah. What it would need to do is talk to node 28, talk to its successor, and get all of the items that it should be serving. So all of the items to which now this new node is the successor. In this case, we create both of these. Okay. Okay. Now, how can we go from any node to any other node? That's the next missing bit. And here we use this idea of pointers or fingers, as they used to be called back then. So every node maintains a routing state, and the routing state consists first from its successor in the ID circle. So every node knows what is the next node on the ID space. That's not enough though, because if you only knew who's the next node in this space, you would need to go around the space one hop at a time to get to anywhere. So if node 9 wanted to read the value for key 50, it would have to go to talk to node 28. Node 28 would go to node 40. Node 40 would go to node 54, and then get the data back to node 9. So you would, in the worst case, you would need to go around the circle to all the nodes. So an ON complexity for this lookup, n being the number of nodes or the number of hops you would do on this network. So that's not good enough. Okay. So in addition to just the successor, every node knows the IP address of m more nodes. This is m being the logarithm of the maximum number of IDs we can have. So in this example, 6. Okay, we would have 6 more pointers every node. These are kept in a so-called finger table or routing table. And the way they work is that the ith row of the finger table of a node points to the node who is responsible, who's the successor of an ID that equals the ID of the source node plus 2 to the I minus 1 modulo 2 to the m. Okay, so this might be a bit hard to parse, but the gist of it is that the first row in this table points to whoever is responsible for your ID plus 1. So that's your successor. Yeah. The second row points to whoever is responsible for your ID plus 2, then ID plus 4, ID plus 8, ID plus 16, ID plus 32, and so on and so forth. And this is all modulo 2 to the m. So if ID plus whatever goes beyond 2 to the m, you continue along on this ID circle. Okay. Now there were systems that were using finger entries pointing forwards or pointing backwards. This is not a big deal here. We don't really care. Just mention here for the sake of completeness that if you had backward pointers, they would point to whoever is responsible for ID minus 2 to the I minus 1 modulo 2 to the m. Okay. So let's see this working here. So let's say that these are the nodes we have in our circle. Yeah. Each one of these, what's happening? Okay. Each one of these knows their successor. So let's say node 36 here knows node 40. Yeah. So whoever is responsible for 36 plus 1, 37, that's 40. Whoever is responsible for 36 plus 2, 38, again 40. 36 plus 4, that's 40, again 40. 36 plus 8, that's 44, and that would be node 44. 36 plus 16, that would be 52, so node 54, okay, and so on. So you have pointers to that guy, that guy, that guy, and I think one more guy over here, and that's about it. Okay. So let's say you want to find the node that stores the file with a key, this is the life or whatever. Okay. First of all, you compute the key of the thing we are looking for. So the ID of this is the life, you hash it, you get a key ID, which is 20. And then you look at your finger table. And that tells you, sorry, what was the ID? 20. Okay. So you want to find, you want to go to whoever node is responsible for 20. So what do you do then? You look at your finger table here, and you pick that entry that takes you as far as you can go without overshooting. Okay. So from 36, the closest I can get to 20 is by going to 4. Okay. This would take me halfway across this network, this ID space. So I'm going to 4. Now 4 has its own routing table, its own finger table. The logic is the same. From here, I want to go as far as I can towards my goal, which is 20, without overshooting. Okay. So the closest I can get is node 14, because then 22 would be after 20. Okay, I would be overshooting. So From here, I go to 14. 14 has its own table entries. What is the one that will take me the closest to my destination without overshooting? And that is 1 or 2, going to 16 then. Yeah. And from here again, same idea. Look at the table of 16. The farthest I can go is there. And now I've reached the point where I've found the node that stores the data for key 20. Okay. And the interesting properties of these systems are that each one of these nodes maintains a routing state, a routing table that has a number of entries that is logarithmic to the number of nodes in the system. And you can go from any node to any other node in a logarithmic number of steps. Why is it logarithmic? Because every time you follow a pointer, you are actually, you will never take the farthest pointer twice. Every time you go from one node to the next, you are essentially moving up this ladder of how far you want to go. Okay, there is a logarithmic number of things in this ladder, so a logarithmic number of steps to be taken to go from any node to any other node. Okay. And of course, this is achieved without global knowledge. So, every node has just this logarithmic state, the finger table. Now, this is exactly the idea used by Cassandra, but with a little change here. So when we had this, with this thing working for peer-to-peer systems, we couldn't afford for every node to know every other node because these systems were huge. So typically back then in a file sharing system, you would have multiple millions of nodes, multiple millions of clients active at any point in time. 2, 3, 4, 10 million nodes. Maintaining an address of 10 million entries, well, you can fit it in memory. The problem is the maintenance costs, because for each one of those addresses, you will need to make sure that they're still alive, they're still valid. So you would need to go and see what's my row 0 in my routing table. Is that guy still alive? Yes. Okay. Is that guy still the successor of what I think it's a successor of? Yes. Okay. Or maybe not. But doing that kind of protocol for each one of those million entries would be highly impractical, especially since in peer-to-peer file sharing systems, there was a very high node churn. So nodes would join and leave fairly quickly at random points in time, and you couldn't really trust them to be around for long. In a cluster, though, like in a data center, that's no longer the case. So Cassandra, the nodes in Cassandra know of all other nodes in the system. Okay, not just a logarithmic number of nodes, but all other nodes. So in Cassandra, the data placement is just like what we said, and this is the idea of consistent hashing. So you hash your storage locations, you hash your items, and you assign your items to their successors in this space. Okay. Now, if we have a large enough number of items, you can expect that each one of these nodes will store the same amount of items, more or less. Okay, because remember, this assignment of IDs is almost uniformly random. Okay. Okay. I'm getting no questions on slide. I wonder whether everything I say is super clear, or whether you're too tired to ask any questions, or whether Slido is not working. Can I ask that at least one of you just post something on Slido, just a hi, to make sure it's working? It's a bit worrying. Okay, it's working. Thank you. All right, so let's move on then with this Cassandra guy. Actually, in Cassandra, there are two placement methods. You can place things using something called the random partitioner, which uses a hash function with random output, just like what we said this is what we would lovingly call brain dead load balancing, because you're not actively trying to make sure that all of your nodes have the same number of items. What you do is you rely on probabilities and statistics. So I'm using a random, I'm using a quasi-random hash function, like think of a cryptographic hash function. So its output will look like random data, and I hope that by using that random, like random looking hash function, my items would be uniformly assigned to nodes. But it doesn't always work like that. So in practice, this is not very good. Why is it not very good? So one reason is what I just said. You cannot really rely on just the statistics to give you perfect load balancing. In practice, and I don't know if like any of you are mathematically inclined, if you do the analysis, you will see that at the end of the day, you do not really expect the distribution of items to be uniform. So you're sort of losing from the get-go. But also, this only balances the, even if this worked perfectly, you would end up with something that has, a system where every node has the same number of items, not necessarily the same load, right? Some of those items might be super popular, and those nodes would be getting the brunt of all of these requests. So you probably want to do something smarter than that. The other way of placing items is by using something called the order preserving partitioner. Now, what's the problem with the random partitioner? The problem is that since your items are assigned to random positions in this circle, there is no other way for you to process a range query other than accessing each one of those positions one after the other. So let's say I have, remember we're storing a table now on top of this guy. So let's say I have rows 1, 2, 3, 4 stored on this overlay, right? Using the random partitioner, I would take ID 1, hash it, and that would go somewhere. I would take ID 2, I would hash it, and that would go somewhere. Same with 3 and 4. They would, with high probability, not be on the same node. And also with high probability, they wouldn't be one after the other on this ID circle. What I mean by that is their order on the ID circle might not be the same as the order of the keys. Okay. So if you were using these fingers to jump around, you might need to go around the circle multiple times to collect all of these items. And this is where the order preserving partitioner comes into view. Here, the hash function is order preserving, meaning that you're guaranteed that if you have two values x and y, and x is less than y, then the output of that hash function for x will be less than or equal to the output of the hash function for y. Okay. Modulo 2 to the m always. These are always modulo 2 to the m. So what this allows you to do is, if you want to do a range query, you can range query from x to y. You can find the location of x, go to the whichever node stores that information, and then just go around the circle to the successor until you get to the successor of y, and you're guaranteed that these nodes are all the nodes, all the relevant nodes storing information for this range. Okay. So this is great for range queries, as we said, but there is a problem with this data placement. And this is the exact problem that the first guy tried to solve. So since now you are hashing based on the key, you have this order preserving hashing, you could find yourself in a situation quite easily, actually, where some of these nodes are overloaded because they have too many items. Okay. And you can think of this case like this. So say you wanted to store a table where the key is domain names, like the example of big table we saw last week. some domain names would have way more pages, way more rows than others. And so the nodes that store those guys would have way more items to store and serve than others. Okay. So how do we solve this? I think we'll see in a minute. Okay. Oh, well, I lost track of time. So I see it's 12:15. We can just go through and try to finish the material, or take a quick break and then spill over to next week. So let me see. Quick poll here on, oh, what's this? Oh, no. Let me run a quick poll on Slido. Okay. Just let me know if you would like us to take a break, or we can just continue. Oh, what happened? There you go. And we're practically taking a break now, right? Okay. So I think there is enough people who have asked for a break. So let's take a quick break. Maybe 5 minutes or whatever. It's 12:18, 12:20. So let's resume at 12:25. Okay. 12:25, we're back. Thank you. Okay. Right. Cool. So let's continue. So how do I find in Cassandra the node that's responsible for an item? Again, as I say an item, but you should think row or collection of rows. Okay. This is a little bit different than classic DHTs because, as I just said a few minutes ago, we don't really have these finger tables because we don't have a highly dynamic network setting. So what we want to be able to do is be able to route from any node to any node without a central global knowledge, without a central mastermind. I can still do it, but we'll see how, right? So in a classic DHT setting, you wanted to have this lack of global knowledge. You wanted the cost of maintaining a consistent routing state to be low, and that's why you only had the logarithmic number of entries in your routing table. And this design decision actually was able to meet both of those constraints. But in a data center, you no longer have the problem of too many nodes. You no longer have the problem of a highly dynamic environment. Okay. So what you can do now is you can actually accrue global knowledge about the existence and locations of all other nodes in your Cassandra cluster. But again, we don't want to have any central mastermind. So we want to be able to do it in a decentralized way. Okay, no master node storing such knowledge. Right, now, the protocol used to do this has a very unfortunate name. No one knew this back in 1990s and early noughties. So we call this a gossiping protocol or an epidemic protocol because of its epidemic propagation. Okay, so in these protocols, knowledge floods or propagates through the network, and eventually all nodes become aware of it. And the way this happens is by, well, gossiping, like or epidemic propagation. So every node that has something in its routing state will typically pick a random neighbor and send all of its routing state to this neighbor. Okay. And then in the next time point, it would pick another random neighbor, send all of its routing state to that random neighbor, and so on and so forth. But as it sends stuff out, it also receives stuff from its neighbors. So every time it receives something, it will take what it has received and merge it with what it already knows. And so the next time it will send an update to one of its neighbors, it will include all of the updates the node has received from its neighbors. So you can see how this is like gossiping, as in, I hear something from one friend, I tell it to my other friends, and the gossip spreads. And it's also how epidemics spread, in the sense that, I got some virus from one of my close contacts, and then I pass it on to my other close contacts. And the way this spreads throughout the network is just like an epidemic. So let's see a bit how this works. So each node picks a position on the ring, and we've seen how it does, right? So it takes its own information, its IP address, port number, whatever else, hashes it, and that gives it a position on the ring. We can call this ID its token, or this position its token. And then this token is gossiped around the cluster. So it sends this ID to everybody it knows. When a node first joins, it only knows, let's say, its successor in the worst case. So it will send the successor its information. And at some point, the successor, who now knows of this node, will send it its routing state, its routing table. So now the node has a complete routing table received from its successor that is sort of, or probably, as close as it can get to a complete routing table of its own, right? But it will continue doing the gossip. So it will pick one of the entries in that routing table in the next round and send its information to that guy. And it will receive something in return. And as it contacts more and more and more nodes, more and more nodes will know of this new node, and more nodes will pick this new node to gossip to. Okay. The actual protocol in Cassandra says that every second, every node exchanges messages with 3 other nodes on the same cluster, with 3 neighbors. Okay, and these messages contain info about themselves, like the ID, their in position, and so on, but also about other nodes they have already gossiped with. And eventually, every node on this cluster knows of all other nodes in the system, and by knowing all other nodes in the system, it knows which arc in this ID ring space every node is responsible for. Okay. Now, when a node joins the cluster, if it actually followed this protocol, it would take a long time to be known by everybody and to know everybody. So what happens is it reads a config file containing a few seed nodes for the cluster, and these seed nodes are just, could be a random selection of nodes from the cluster, or it could be some specific nodes that are, maybe higher spec, more reliable than other nodes, and are in the cluster just so that you can find at least a few nodes that will give you the first information, the first glimpse of the state of the cluster. Okay. Now, what happens if a node leaves? So this is standard consistent hashing stuff. If we had node B here, node B would be responsible for all items that fall in this arc. So if it wants to leave, all it needs to do is take the items it was storing, and pass them on to C, to its successor. Okay. Why do we do this? Because if anybody else was looking for that item, it would use the routing state to route to this place, because looking for the successor of the item. But if this guy is no longer around, the successor of the item is C. Okay, so in essence, what this protocol does is it places the items where other nodes would go looking for them. Okay. So what happens if a node crashes, right? So if B was holding some items and all of a sudden it goes boom. With just what we've said so far, this would lead to data losses, because this node is the only node holding these items. If it dies and it doesn't move them on to its successor, then these items are lost. How do we solve the problem of data loss and reliability here? Right, we've seen this in the past multiple times. What we do is replicate. Yeah. But where do we replicate now? So where would it make sense to keep a copy of this little red item? And it would make sense for us to keep a copy of this item where people would go looking for it. So where would people go looking for it? The successor. So now I have one copy. Yeah. And what if the successor dies? I can place a copy on the successor of my successor. So that's 2 copies. Now I have 1, 2, 3 replicas. Okay. Now that's just one way of creating replicas. So again, the standard degree of replication in the paper is 3, just like with HDFS and other systems. And that means that I go clockwise and place more replicas to my successors, right? So all items that fall in A to B are stored on B and C and D. All items that fall in B to C in this arc are stored by C, but also by D and by E. Okay. So this is the default replication scheme, but typically these nodes might have different capacities, and also these nodes might be responsible for arcs of different size. Yeah, and some of these arcs might be more popular than others, and so on. So this replication scheme gives us one of the properties we're looking for. It guarantees that we will have at least that many copies. It doesn't, though, guarantee that the load will be balanced. Okay. There is nothing though that says that these nodes should be in the same data center or even the same rack. So they could be in different racks, different data centers, and so on. It's all the same for the protocol. Now, if a node fails, let's say node B fails, and someone is looking for something in range AB, yeah, they would go there, would not find B, would fall back to the successor of B, and they would find the value there. All right. Okay. Now, whenever a neighbor detects a failure, so let's say A or C here hasn't heard back from B in a long time, or actively tried to access B and B was not responding. So they detect that B is no longer there. So then what they need to do is try to ensure that the replication factor is met. Okay. So then if C detects that B is no longer there, C will create an extra replica of those keys over there. Okay. The keys in A to B are already replicated in C and D. That's only 2 of the 3 replicas I need. So C will take it on itself to create an extra replica of that range in node E. All right. So the successors, its successor and the successor of its successor. Okay. Now, no replicas can ensure high availability, but they also help with load balancing to some extent, because since these replicas are all there, you can pick any of the 3 when you try and read something. Okay. So the replication protocol we just saw is the simple one called simple snitch. So we just go to that many successive nodes and store the item we're storing or updating. There is another protocol, another scheme called the rack inferring snitch, and this looks a lot like HDFS. So it tries to infer the data center and rack from the IP address of the node, and so the first replica will go to another rack. The second will go to the same data center but a different rack, and so on and so forth. Okay, so what this guy tries to do is he tries to maximize the availability by storing the replicas at different failure domains. There is something called the property file snitch, where you tell it exactly what to do. There is one more for Amazon EC2. There's actually way more than this these days. I just wanted to mention this to see that we can do stuff that looks like HDFS, that is rack aware and data center aware. It's not just this simple, like brain dead way of creating the replicas. So for every item, there is a coordinator, and the coordinator is the actual successor of the item's ID. And it's the coordinator that oversees replication. So for all keys that fall, for example, in this arc here, where it says key, the first green node down here is the coordinator, and it's this coordinator's responsibility to make sure that there are 2 more replicas, and those 2 replicas are kept in sync. Okay. Through this gossiping protocol we said earlier, every node knows what node is responsible for each arc. So every node knows exactly the locations of all replicas for all objects, or at least if things don't go wrong here, if nodes do not like disappear or join, the gossiping information is enough to tell you exactly where each copy is stored. And if something does change, the gossiping protocol will eventually propagate that change to everybody. So eventually everybody will know all locations of all replicas of all objects. Okay. Now, how about load balancing? We've touched upon this problem a number of times so far. We've said that some items, some keys, some items, I'll just use the term items. Some items might be more popular than others. Some arcs here might have more items than others. Some arcs might be larger than others. Okay, so how do we balance the load? And of course, there are different strategies. One of the first ones that were, this virtual nodes idea was actually proposed again in early 2000s, if I remember correctly. Probably even before that, probably late 90s. And the idea is that every physical node, so every machine that joins this cluster doesn't have just one token, just one ID. It assumes multiple IDs, and these are picked randomly in this ring. Okay, and in doing so, you actually create more partition points, and hence the load is partitioned across more of these virtual nodes. Okay, this isn't actually the best solution. This is just one step forward, right? From where I said every node takes one ID in the space and is responsible for only that arc, what I say now is every node takes multiple IDs in the space. So I have more smaller partitions of this ID space. And in doing so, I hope that these nodes will have load that is balanced more or less. Okay. So this is what this figure tries to show. We have Q equal-sized partitions, S nodes. Each one of these S nodes takes Q over S tokens. So each one of these nodes is responsible for Q over S arcs in this space. So let's say node 1 takes this arc and this arc and this arc. Node 2, which is the green one here, takes this, this, and this, and so on. So all nodes have the same, approximately the same number of little arcs that they're responsible for. And since this number is higher than the number of nodes, or higher than previously, there is a better chance that the load each one of these takes will be the same as that of others. Okay. Now, if you have a system where nodes are more powerful, these nodes could take on more of these partitions than others. So in this example, you will see that the blue node has 4 of these partitions and the yellow node has 4 of these partitions, whereas there are 3 partitions for the red node and 3 partitions for the green and the orange node. Okay. So these nodes in the system can take this decision on their own, say that I think I'm powerful enough to hold X partitions and then take X partitions. And if they're not powerful enough, they can relinquish some of these partitions back to the system to be assigned to other nodes. Okay. So as I just said, these virtual nodes help with load balancing in 2 ways. First, they reduce the arc size inequalities because I have more of these partitioning the space, and it's a better probability that these partitions are not that much different. But they also address the node heterogeneity issue. So the nodes that are more powerful than others can take on more partitions, and so take a larger share of the load. And that's still fair because they are more powerful. Okay. And now for the last bit here, which is consistency. So in Cassandra, we said that Cassandra implements Bayes, so eventual consistency, but it also offers this tunable consistency option. So the problem is, the issue of consistency is, I go to some replica and read something. Is what I read the most recent version of that item? Okay. So remember, there are several replicas. So how can I know if I just go to one replica? Yeah, how can I know if that replica is up to date or stale, right? Can I read from any replica? Or should I pick the replica I read from in some specific way? Do I maybe perhaps need to read from several? And is this issue related to how many replicas are updated during writes? Okay. So, I mean, all of these questions actually lead to a replication and consistency protocol. Okay. So, before we move on to see how this works in Cassandra, just a little note. Some applications are okay with reading stale data. Okay. We've seen some of this in the past. Okay. So, for example, if you had something like a chat, it would be okay if some people in a chat saw messages later than others. So if they had a somewhat inconsistent view of what the chat is, or if you had something like a basket in an online shopping application, it would be okay if you add something to your basket and then you go to look at it and the items in the basket are ordered in a different way than what you added them. Okay. So these are just two examples, but there might be more examples. I'm sure that if you sit down and think, you'll find more examples where reading stale data is okay. Okay, so let's see how replication works. Typically, in replication, I mean, the easiest thing to do is a primary and secondary scheme, where one of the replicas is named to be the primary or the master, and the others are secondaries or followers. Okay, so in this case, what happens is that whenever a client wants to do a write, it will send the write to just the primary. The primary will commit the write locally. Okay, so it knows that now the new state for this variable is X, what my client sent me. And it can tell the client that it's all good. I now have the latest state. And in parallel or in the background or afterwards, lazily, it can propagate the write to the followers or the secondaries. All right. Now, what happens in this case if the primary goes down? Well, if the primary goes down before it acknowledges the write, then it's, I mean, okay. Actually, I don't think I want to get into this because we don't have enough time. But depending on where the failure happens, there is possibility for either data loss or lost acknowledgements or double writes and so on. Okay. Now, in this case, let's assume that the primary doesn't go down and the information has been sent to the replicas. Now, some of these replicas will receive the information before others. If I choose any replica to serve the request, am I guaranteed to get the latest? And the answer to this is no. If we just follow the protocol that is on the screen right now, there is no guarantee the replica will be current. We need to take extra steps. Okay, but this is the eventual consistency model. Okay, eventually, if I leave the system alone long enough, eventually everybody will agree on the same state. Okay, this is practically base. We can take this a step further. So instead of having primary secondaries, we can have consensus, a majority consensus. So now I have a bunch of servers, these being replicas of the information I want to update, and they are all equal. There's no primary, secondary. The client will send the write to at least a majority of the replicas. So if I have 4 replicas, what if there is a failure? Okay, that's a good question. I'll pause this for a minute and address the question that says, what happens if there is a failure before the system becomes eventually consistent? There is no guarantee given there. Okay. Some of these failures might lead to data loss. You see how these systems take steps to make sure that probability of that happening is reduced, but utterly there is no guarantee that that will never happen. And so you can have data loss or inconsistencies. Okay. If you have an application that cannot tolerate data loss, cannot tolerate inconsistencies, perhaps these systems are not the best option unless you run them in a mode that is highly consistent but not as available. And we will see an example shortly. So here the client wants to write something, it will need to write it to at least a majority. So if we have 4 servers, it needs to send the write to at least 3. Okay, typically it will send it to everybody, but at least 3 of these guys need to confirm the write was successful. Okay. Each replica applies the write locally and increments a local version number. So it says, now, my copy has been updated that many times, or my copy was last updated at time point X. The client waits to receive acknowledgements from at least a majority of these replicas, and then it will assume the write is successful. Okay, so this write is presumed to be committed only if a majority of replicas participate. Okay, and what this does is it implies a two-phase protocol. First, you ensure that at least a majority of replicas is available. If not, you abort the write operation. You say, I cannot do this right now. And once you have ensured this majority, then you send the writes to at least a majority of the replicas. Okay. Now note, this is not a majority of surviving replicas, it's a majority of the replicas. So if you have an item that has 4 replicas, you need to be able to write to at least 3 for the write to be committed. If you are supposed to have 4 replicas and 1 is dead, and you only have 3 replicas surviving, it wouldn't suffice to send the write to 2, which is the majority for 3. You would need to send to 3, which is the majority for the total number of replicas. Now, a read, on the other hand, would go to a majority of replicas again. Okay, so if you want to read something, you would need to go to at least 3 out of 4 in this case. And the reason why you do this is that in that way, you are guaranteed to have an overlap of the writes and the reads, right? So if you write something to x1, x2, x3, and then you, when you read something, you read x2, x3, and xn minus 1 here, whatever, at least one of these nodes that you access will have seen the latest version. And so when you access all of them, you get back multiple versions, and you will keep the latest one as the most up-to-date. And there are other mechanisms that will kick in that case to make sure that all the other nodes now go and get the most up-to-date version from the node that has the most up-to-date version. So this consistency level now has serious performance implications, because if I can just read the replica that's closest to me, that will have the smallest delay. So reading from any would be great. And waiting for just one replica node to return the data is much faster than waiting for several. Yeah. So again, a read from 1 would be great. So I don't want to have to read from a majority. I want to be able to say, I want to read from any, or I want to read from 1. Okay. But still, I don't want to lose consistency. And for writes, writing to 1 or fewer replicas is much faster than writing to many. Okay. But having a primary replica has the disadvantages of both bottleneck and possibly reduced consistency. And so I don't want it. I want all the good stuff of the single replica, sorry, of the primary secondaries, with all the goodies of the majority quorum. So this brings us to quorum-based replication, which is a generalization of majority quorum. Okay, here I say that every time I will read from R replicas. This is my read quorum. And every time I write, I will contact W replicas, at least W replicas, which is my write quorum. Okay. And at any point in time, these two conditions must hold. W plus W greater than N. That means I write to at least half of the replicas, and R plus W greater than N. That means that there is a guaranteed intersection between reads and writes at one of the replicas. Okay, and in this way, all reads are guaranteed to see the latest version, bar some weird edge cases, and I will post something on the Moodle forum for these edge cases. But what this gives us is this tunability. So if I have read-intensive objects, I can reduce R, and that means increase W. So if there is an object that I write infrequently but read very frequently, I can write to more replicas, and that gives me the opportunity, that gives me the possibility of reading from fewer replicas. Okay. If I have write-intensive objects, I can do the other way around. I can tweak W to be smaller and increase R, so that again I'm guaranteed this intersection of reads and writes. Okay. And Cassandra lets applications decide among these options. So for writes, I have these 5 basic levels of consistency. Level of 0 says I have no guarantee. I'm not guaranteed to write to any. The level of any says I will write to at least one node in the cluster, even if that one node in the cluster is not exactly the one that's responsible for the item I'm writing. 1 writes to the guy who's responsible for the item I'm writing. Quorum will write to at least half plus 1 replicas, and all will write to all replicas. Okay, and then on the read side, I can read from 1, or I can read from a quorum, so half plus 1, or from all. And now remember, these half plus they can be tweaked. I can tweak the R and W, and so this can be other than just half plus 1. These are then expanded when we have multi-data center operations. So there is a local quorum that only looks within local data centers. And there is an each quorum that will look at all data centers, but will run this protocol only within each of these data centers, not across. Okay. And just for completeness, there is this HH mentioned here for the any write level. And HH stands for hinted handoff. It's mentioned in the paper. And the idea is that if a node cannot apply a write directly to where the write should go, because that node is unavailable, then it will store a node. It will actually describe the write request and will store it on some other node on the cluster, and that some other node will be checking for the actual destination of the write, and when that write comes back, it will hand over the write, it will relay the write. Okay. And read consistency levels are just like we saw, with the addition of the 2 additional quorum levels for multi-data center operation. And I think that pretty much sums up our coverage of Cassandra. So Cassandra versus HBase, these are both instances of LSM trees. They both have per 5 indexes, Bloom filters, compaction rounds, the whole lot. The data model is pretty much the same. Data is again partitioned horizontally. Well, there are no such things as region boundaries in Cassandra, because we have the partitioner that's applied on a per item basis, and data is replicated across nodes. If we need to change the partitioning for an existing table, we will have to rehash all items in the table. So that's an expensive operation. You'd better pick your partitioner correctly the first time around. Other than that, Cassandra is generally faster because of the way the protocol works, but also because it's not sitting on HDFS. So when you go to a node and you want to access the data that that node is responsible for, that data is stored locally on that node, typically. Cassandra has no single point of failure, so there's no master. Each node is a possible master. Actually, each node is a coordinate or a master for the items that it stores, that it is responsible for, sorry. It can easily support multi-data center deployments. And this final one is in case you actually get to use HBase or Cassandra. Cassandra is somewhat easier to use out of the box, although HBase is catching up. And that's all there is to say about Cassandra today. And with that, we'll finish for the day. If you have any questions, please feel free to post them on the forum. Today we had the final quiz, will be open until 6. Next week is, I believe, our last lecture. We'll do a quick recap of what has been discussed throughout the semester, and have a look at possible future directions for research in this area. Yeah, no quiz next time in case anyone asks. Yeah, so thank you very much. Have a nice day or night, and see you next week. Bye-bye.